featuring Alex Forbes, Senior Smart Water Engineer from Anglian Water, and also one of our very own RiSWP ambassadors. So really excited to be featuring Alex today. But before we get started, just a little bit more about who's hosting this call, who's here with us today. So like I said, feel free to introduce yourselves in the chat. But for those of you who are unfamiliar, SWAN is a global nonprofit forum that brings together water utilities, regulators, startups, students, young professionals from all around the world. And we're really here to help advance the smart water sector. And as you guys can see here, we have our smart water ecosystem. And one thing that you can notice right here is rising professionals are a really important part of our smart water ecosystem at SWAN. And RiSWP is here to really help empower young professionals, help them grow their smart water careers. And that's what we're here for today. So just before we dive into our programming, just a little bit more about what we do at RiSWP. So really, we're here to help upskill the current workforce by providing smart water courses, webinars, just like this one that we're having today. We also have a really extensive career development page, a career development portal full of really great resources for helping you find your first or maybe your next smart water role. Like I said, some different smart water courses, our ambassador program, which is a year-long leadership development program, and our mentorship series, where we bring in all different sorts of folks from across the smart water sector to really provide their background experiences to share with us to help us really grow ourselves in our smart water careers. So just a few upcoming events we wanted to share. So we do have the holiday season coming up upon us. So we are having our annual RiSWP Happy Hour. And this year it's going to be all about meeting the RiSWP ambassadors. So please, we welcome you to join us, connect, celebrate, network. That's going to be happening on December 15th. We'll drop the link in the chat also to register. And then also, we want to hear your voices. We really value different perspectives at SWAN. It's really important to us whenever we have an event to have diversity represented on our stage. And that's also age diversity. We don't want to just see a bunch of maybe senior level professionals. We want to hear from folks all across their journey. So we have a few different events coming up. We have a Cape Town workshop happening in March. And then we're going to the US, to Tampa in June for our 16th annual Smart Water Conference. For both of those events, the call for abstracts is open. So again, we'd love to hear any of your relevant case studies or stories, or maybe some proposals for the Young Professionals Workshop at the SWAN Conference. So definitely feel free to submit an abstract. If you have any questions, you can always reach out to me or anyone on the RiSWP leadership team, and we're happy to help guide you. And also, maybe if you're not sure how to write an abstract, or you've submitted a bunch, but maybe they keep getting rejected. We hosted actually a really great RiSWP workshop last year, and it was all about mastering abstract writing. There's some really, really great tips in here to help you boost your chances of getting your abstract accepted, not just at SWAN events, but really across the global water sector and all the different events going on. So we'll also share that link with you guys in the chat. And now I'm going to pass it over to Naisargi, one of the members of our RiSWP leadership team, and also the host of the RiSWP teaching series. So thank you guys so much, and thanks for joining us.
All right, thank you, Sandy, and welcome everyone. I wanted to thank you all for your time today, and one thing I will promise you, we're going to keep it very interactive, and we also have a really fun exercise coming up. So I hope you stay on for the exercise, because that's something I'm most excited about. Let's go ahead and get the slides going. Alex, do you want to start the sharing, because that one has your cool introduction. All right, so we've been doing this series since earlier this year. It's a SWAN 5-layer model. We are currently on layer 2, which is today's call, sensing and control. The previous layer, which is the layer 1, physical assets, was recorded and it is available on the SWAN website for you to go check out. But for now, let's go ahead and get going on layer 2. For today, our speaker is Alex Forbes, who is a senior smart water engineer at Anglian Water in the UK, and he's also a Swan RiSWP ambassador. So he's really in this at this point, and he brings 6 years of experience developing patented analysis tools for potable and wastewater systems. He leads the Rising Force Mains tools. I'm kind of like reading these words here. Rising Force Main tools in Syrinx Radar platform, which I don't, being doing what I do, I don't know what that is, but maybe we'll give Alex a chance to explain that. And he's undertaking transient analysis and root cause analytics, which I do know what that is, for reducing costs and detecting breaks faster. He now focuses on enabling Anglian Water to develop systems thinking, transient analysis, peer recondition assessment, and embedding these within their regular practices. So with that, take it away, Alex.
Brilliant. Thank you so much, Sandy and Nasagi. Really appreciate the introduction there. And really nice to see you all as well this afternoon. So to kick us off then, yeah, really awesome introduction. As Nasagi says, I've been working in the industry for about 6 years, a lot with the sort of the layer two that we're looking at. Syrinx, as some of you will know, is a manufacturer or was a manufacturer of pressure monitoring equipment. So very much up that sort of on that level two, yeah, that layer two, sorry, within your five layer model. So we'll kick off with the first of the interactive points. So there's you should see you've got your QR code there on the left, and there's a couple of questions to answer here. So the first one is, what examples of layer two can you think of? Bearing in mind we've not been through anything yet. I imagine you have probably a pretty good understanding already based on the name. So I'd love to hear your thoughts. And then we have a second question. Where do we use that in our potable water network, wastewater network? What areas can you think of that we use it in those? So you can scan the QR code there on screen. You'll also, my colleagues will pop the little link there into the chat as well for you if the QR code doesn't work. And we'll give you just a couple of minutes to fill those questions out, get your thoughts down, and we'll have a little look at the word cloud that comes out the back of it. So as a note while you're filling that out, the word cloud that's generated out of your responses, we'll snip it and we'll pop it onto the presentation as well. So when we're looking back, and once we've been through this discussion, you can then go back to the presentation again and you can see how many of the answers in the word cloud come up in the presentation. And equally, is there anything that maybe wasn't mentioned in the word cloud, which we talk about later on?
I will say, Alex, that I did submit for your presentation to update. I think you're going to have to click refresh to see what responses are coming in.
Gotcha. Give me 1 second then. Yeah, absolutely right. Okay. Brilliant. So I've got 3 responses so far. 4. Cool. So yeah, some really interesting points there. So I'm not terribly surprised that flow has come up twice there as quite a major one. Awesome that we're seeing pressure come in there as well. Ultimately, those are your sort of your key physical properties of your network that move the water from point A to point B. We want to know all about flow and pressure. We also bill people using flow, so it absolutely makes sense that that would be coming up. We have a look at where we find it. Where do we use it? We've got loads of different examples here, some really awesome ones as well. Treatment plants in the network, water quality is the biggest one there. Obviously, that's something that we're certainly in the UK, we're very regulated on. So absolutely that should be coming up. Brilliant. You've got noise there, a really interesting point, something I didn't know whether we'd see it or not, and I'm really pleased that we've picked that one up. Metering areas, PRVs, districts, some really good answers there. So what we'll do is we'll carry on. We'll have a look at the 5-layer model itself. So ultimately, what is it? What's the high level framework that we're discussing here? And how does that layer 2 then fit into it ultimately? So you've got your 5 layers there. You've got your physical assets, your sensing and control, collection and communication, data management and display, and data fusion and analysis. And ultimately, each one of those layers feeds the layers around it. So we're talking about our sensing and control, which sits on your physical assets, and we'll talk a bit more about how those interact throughout the presentation. Now, this framework is particularly powerful because, and you can see some of the examples there, it gives you a really clear framework upon which to build a smart system. So the gap analysis and the being able to identify potential are two really key aspects, and something that certainly we work with within Anglian is you're able to say, well, we've got however many physical assets, we've got however many kilometers of pipe. Do we know what the pressure is like in all of them? Do we know what the flow rate is going through them? We've got however many pumps. Do we know the pressure that they're generating? Do we know the power that they are consuming in order to operate properly? Do we know the flow rate that's going through them? And so we're able to then look at these layers and say, well, we've got loads of layer 1, as one would expect. But do we have enough layer 2 in order to supplement the understanding of that layer 1? And then we can come up to your following layers as well. We can say, well, we've got loads of sensing and control. We can go and have a look at the meters. We can go and have a look at the dials, the pressure gauges that we've got. We've got plenty of people going out and taking samples. How do we collect it, and how do we bring it back up to something that's actually accessible to users? And this is that framework coming into play. You can really see how beneficial it is for that sort of gap analysis and that investment and potential that you can get. And one of the things I really like about this as well is you've got your protect and your prepare there, and these are really key. Ultimately, we know, well, hopefully we know how our network is going to change over time, new developments. Maybe we're going to be changing the way that our networks operate. Maybe we're going to be taking storage points in and out, or treatment works. And so we can then go, well, what do we need to put in place to understand the impacts of that? Maybe we've got all the sensing we need, but are we able to display it effectively? Is it accessible to the people who need it? So it's a really valuable framework to build your smart water system around. So last time as Nasagi said, we had a really great presentation from Jennifer Morales from the Public Works Asset Manager from the City of Omaha Public Works. I'd really, really suggest you go back and have a look. It was a really fantastic presentation that she gave. And she was, as suggested, she was talking all about moving the water from A to B, or indeed preventing it from moving from A to B, with your valves. And it was a really insightful presentation. And one of the things you'll see with this presentation is that your layer 2 is built on top of your layer 1, just like we see in the framework there. Your layer 2 is about interacting with it. So we'll see a lot of that layer 1 coming into the presentation today. We can see that your layer 2 is going to interact directly with your layer 3, sending that data up and down. But also, let's say you've got a PRV. Maybe your PRV is being controlled from a pressure sensor out in the network. So that pressure sensor is going to have to send your data back to your layer 3 or via your layer 3. That's then going to come back into your control of your PRV controller. And that PRV controller is then going to influence that physical asset and be able to tell it, okay, well, we need to open or close a bit more than you currently are. And then your physical asset's going to have its own physical properties. So those are things that we can measure using our sensors, which can then feed back into our control. And this is really the core of what we're going to be talking about, is that sensing and controlling. So I've got a couple of examples here. These are a type of sensor that we use in Anglian. It's not the only type of sensor that we use, but we have this one. This is a pressure sensor specifically. So this is what we might find out in the network. We might find it near our pump stations when we're measuring pump pressure. We might find it on a PRV, a critical asset. And these sensors are able to detect, like it says there, a physical property to do with that layer 1 asset. You've then got your controllers there, and these are 2 photos taken by myself and my colleagues at Anglian. Your controller is able to affect how that physical asset is going to operate, how that layer 1 is going to operate. So in this case, I've got 2 examples. The one on the left is a PRV controller. You can see it attached to the wall there. The PRV itself is able to actuate, because it's a PRV, it will do what PRVs do, but the controller is able to tweak that control and make it operate more effectively, more efficiently, maybe even change the set point depending on the situation the network finds itself in. And then you've got your pump controller there. In this case, it's an inverter. But we can then have those controllers, instead of just starting the pump up and letting it run, we can change whether it's running at one speed or a different speed, depending again on the situation that the network finds itself in. So we've got another audience moment, so I might need to refresh this one. But what are some of the examples of drinking water sensors that you can think of? Again, I'm sure you've come across plenty of them in the work that you've done so far. So let's just get a little word cloud. What are some of the most common ones? Now with these, again, you can scan the QR code and we'll grab the word cloud once we're finished. But I've made this one so you can submit more than one response if you wish. So you can put in, your pressure sensor and then something else and then something else and then something else. So please feel free to submit more than one. I will give it a refresh in a moment, and we will give it, let's say, another minute or so. Just give it a quick refresh, 1 moment. Perfect. Got some responses coming in. I suppose this isn't terribly surprising, but the big word here is sensor.
I love that. I feel like we almost gave it away in the question.
I think we may have, yes. But again, we've got some really awesome ones that have come in there. Your hydrophone, a really good example. Yeah. No, really good example. Something that we use for leak detection.
Is that what it's called in the UK? an acoustic logger or something. Is it what it's called, hydrophone?
It depends on how you're measuring it. From my understanding, a hydrophone goes in the water, hence the name. But so we
Uh,
used to, the company I used to work for also had geophones, which were connected to the outside of the pipe. But ultimately, they both measure acoustic signals. That was my
Interesting.
understanding anyway. That was the way that Cyrenix did it. I'm not sure if that's I don't know if that's Cyrenix unique though.
That's interesting.
Cool. I think we've got some really awesome answers there. Lots of pressure. Really glad to see transient loggers coming in there as well. A personal favorite of mine. But yeah, brilliant stuff. So we got awesome. Yeah, again, your critical points are a really interesting one. I'm interested in the network sensors. If that's a specific type of sensor or just like a generic collection of sensors that we might have out in the network. Cool. All right. So we've got a couple of examples here. This is by far and away not an exhaustive list, and the list continues to grow as new and exciting things that we can measure come on the market. But this is a small list of some of the types of sensors that we regularly see on our networks. So as pointed out earlier, you've got your flow sensors and your water meters as well. And we specify that difference, at least ourselves, because our flow sensors are generally providing us with that time series data that, well, this is what the flow is right now, and then we'll take another sampling in a minute, 2 minutes, 5 minutes, however long. But then you've got your water meters as well, which really provide us with a totalized flow. So how much of that flow has gone through the meter, so we can do things like leakage calculations or billing or things like how much water has the treatment work produced over a given period. But ultimately, they're both just measuring how much water is flowing through them. You've got your pressure sensors there. Now, we saw a few interesting examples on the word cloud just a moment ago with the transient logger, critical point pressure sensors as well. Ultimately, as with all of these, there's some nuance that comes into this. The analogy I like to use is all of these they're tools and they have a purpose. And ultimately, just because something's a hammer doesn't mean that it's suitable for hammering a nail into a wall. You wouldn't use, say, a rubber mallet to hammer a nail into a wall because you'll just damage the mallet, or a sledgehammer for that matter. So there's a correct tool for the job, and that applies to sensors as well, depending on what the goal is that you're trying to, the goal of the meter that you're trying to put in. Now, you asked the question about acoustic sensors and noise loggers, and really, I think you've certainly within Anglian, we refer to them as acoustic sensors or noise loggers, depending on whether they are essentially depending on how the data that comes out of them is used. But again, they're both measuring acoustic signal, and that acoustic signal then either gets returned to us directly or it gets returned to the third party portal. So this is one of those examples, and we'll talk about it later, where we may not be able to measure something directly, but we can infer it based on calculations that we do. So your acoustic noise loggers, same with leaks, and this is leakage. Your acoustic noise loggers are able to tell you roughly where a leak is in your network by listening for it. And you can compare the two different acoustic signals to then work out where that leak is. So we're not necessarily going directly to the leak and going, it's right there, but we're able to infer it based on like a collaboration of different sensors. And you find that all the time when we can't measure something directly. We've got some water quality sensors there. That's a really big one. As an example, we put chlorine monitors on the outlet of water treatment works to make sure that we're not overdosing chlorine, to make sure we're not putting anyone at harm's way, to make sure that the water is of a good enough quality to actually send it out to the customers. So that's great. You've got your condition-based monitoring there. This is another one where we can measure the physical properties of, say, the pump, but we can combine those together to then give us faults or the causes of those faults or the severity. And last but not least, we've got our level monitors in there as well, measuring the water level within things like storage points, or indeed when we're looking at water treatment works, there are certain times there are tanks where we need to know how much water is in them, and we'll use those level monitors. Now, one of the key things, and we'll talk about it more later, one of the key things is that within water recycling, within wastewater and stormwater, we use much the same set of sort of standard sensors. It's just, again, the process has changed a little bit. So maybe instead of using a flow sensor, we'll use a level monitor because we don't have the water in the pipe has an air pocket in it, so a flow sensor wouldn't work, but a level monitor does. So ultimately, we're trying to measure the same stuff. It's just with the same sensors, it's just we're doing it in a different way. So we've got one more moment. And this one is what are some of the examples of drinking water controls that you can think of? So here we're not talking about when we're trying to sense something, talking about what can we control based on the data that we've gathered from those sensors. So we'll give it a minute or so. Again, same with the last one. Please submit more than one answer. Just keep adding them. We'll give it a minute or so, and I will refresh this one as well. Just give it a quick refresh. Brilliant. I'm there's only one response so far, and it's just the word tap, and I think that's wonderful. That's fantastic.
That's me. I wanted to mess with everyone.
Brilliant.
But that's just something I thought of because like tap is a control. And so if we think about it, it doesn't have to be overly complicated things. I mean, it's all important, but a tap is also control. We control something in the system.
Yeah, yeah, absolutely. And there are take flushing as an example.
Hmm.
We will sometimes have to, or we'll have automated flushing. Um, Granted, it's bigger than just your everyday garden tap, but it ultimately, yeah, you're just pulling water out of a network.
I see distribution network.
Yeah,
So the entire network. I never thought about it that way.
it's an interesting point.
It is.
Yeah, yeah, dosing is a big one.
Dosing control,
Yeah,
disinfection.
yeah,
So those are all quality related. Then we've got filtration, also quality related.
yeah,
Real
absolutely.
time.
No, got some awesome responses there.
There's just a singular letter G.
There is just a singular letter G. Auto valve is a nice one as well. Yeah. All of them are great.
Cool. Fun.
Yeah, thank you all. Really, I really like that. We'll get a snip of that afterwards as well and just pop it onto the presentation so you can look back at it. So again, this is far from an exhaustive list of different types of assets that we might want to control. But this is a good example of some of the most common ones that we're looking at. So you've got your pumps, your pressure reducing valves. We discussed those earlier. But equally, you've got things like your air valves. Air valves can often have sensing on them, and they can have ways of closing automatically if they detect that something's going wrong. And we talked about it, or it was in the word cloud, and I'm really pleased that it was. You've got your chlorination and disinfectant there as well. So a really key point that we do often automate there as well. Now, a key sort of understanding for this bit is you can see that at the bottom. A smart network can adjust its operation to the situation it finds itself in, but it first needs to know the situation it finds itself in. And this is why your control and your sensing, they go hand in hand. They absolutely have to. If you don't know what you're working with, how can you control for it? So here's some of the things that go wrong with the sensing and control. And the first one is something I have been personally guilty of in the past, and it's something that we should all remember, is maintenance. Maintenance. Everything will go wrong. And that's okay. It's just a part of life. But poor maintenance can give you no data whatsoever, which is not great. It means now we've got an expensive paperweight. But on top of that, and I would argue what is worse is getting erroneous data. If the data doesn't mean what you think it means and you make a judgment call on that, you can end up causing more damage than you actually saved. So it's really important that you understand that maintenance burden and you're able to put something in place. You can see there, sometimes it's not obvious that your sensor's malfunctioning even. Making sure that you have a nice, robust way of checking it against models regularly, doing your calibration on your meters, that sort of thing. It's really important. And we'll talk about data quality a bit later, but once you've lost that trust with the people who are using the data, it's very difficult to get it back again. One of the things that I'm really pleased that we're pointing out here as well is requirements for operation. Things like power. So you can see I've got an example here of a PRV. PRVs themselves are powered by water pressure. They don't need any power other than whatever's going through the PRV itself, which is great. The controller does, usually. I think it does. So certainly your sensor will. So, but getting, say, a mains power connection to a chamber out in the middle of a field, it's never going to happen, at least not cheaply. So we have batteries, we have solar panels, that sort of stuff. But we have to consider, is this the right tool for the job that we're trying to get it to do? And do we have the ability to get whatever we need to get that control and that sensing? An example that myself and some of my colleagues are going through at the moment is we're trying to get some pressure sensors installed on pumps on the downstream side of some pumps. And because they're in pump houses, there's plenty of power. That's not really the issue. But what we are having to really consider is, can they get signal? Can we get the data from the sensor back to where we need it? Because if not, it's kind of no point having it there. And the last one there is accessibility of control. You can see a poorly controlled asset can be as bad, if not worse, than something that's just controlled simply. There's absolutely nothing wrong with running a pump in hand, for example. But we can't just let anybody do it because they may not know what they're doing. Equally, it comes back to that maintenance. If you don't arm the person who's making those changes with meaningful, real data, they may well make the wrong judgment call and cause a bigger problem than if they hadn't done anything. So yeah, really key that all of this we keep it up to date, we keep it maintained, and we understand what it is that we're working with as we go forwards. So we've got a little worked example here. call it Smart Water in Action. It's not a real story, it's just an example. But we've got a little town. You and I, we're engineers in the optimization team of this little town, Utilityville Water. It's a small water utility which has a number of different distribution zones. One day, the network manager comes to us and asked us to help with a problem that they've been having over the last few months. More and more complaints of low pressure and water quality have been coming in from one of the distribution zones. What should we do to understand the problem? So you can have a little think about what you might do. What would be your first port of call, maybe? Maybe think of what the first 3 things that you might do. You can see all the disgruntled customers there in the bottom right. So in this case, maybe what we do is we go and verify that those problems are indeed happening, and we verify how big of a problem they are by taking pressure and water quality measurements from data loggers or from manual tests from our technicians. Maybe what we do, we know that this area is probably fed by this water tower, so we can install a water tower level monitor on the tower, make sure that we're not getting low water level in the tower. And then we can install some pressure and flow monitoring on our pump set as well to make sure that we're actually delivering the flow required to get into the tower and to get all the way up as well. So through that piece of work, we've verified that the complaints are real and they're widespread across the network. We've identified using other means that there's no cascading distribution zones and that all of the water is coming through that tower upstream of the distribution zone. We've also identified that the water quality problems being reported are increases in turbidity as well. So we've discovered that the reported drops in pressure and the spikes in turbidity are because the tower is at its highest level getting critically low. The pumps feeding the tower run at a fixed speed, one at a time, but continuously. How could we help control the tower level better without installing any new valves like a PRV? Again, just have a little think. Maybe what might you do? Give me 3 things that, or have a think about 3 things you might do, might consider to do with those pumps. So first thing we can do is control the standby pump to kick in if the tower level goes below a certain point, for example. We could measure the flow out of the tower, compare it to customer demand, and measure the leakage out the back of that. And finally, we could install some noise loggers in the downstream distribution zone to look for leaks. Ultimately, what we're looking for here is why is that tower going so low all the time? So we install the pump control and we've tasked our leakage colleagues to conduct a study into the network. And they found a few small leaks which they could repair at the time. And the solution that we've put in place works well for a few months, until one day when the second pump turns on, the pressure reading 15 minutes after the pump starts shows the pressure going down and the flow rate goes up. You hear that there are now some new customers who are complaining about water flooding into their gardens. So out the back of that, we identify and fix a pipe beneath their properties, which was very old and very leaky, which has burst. And it just couldn't handle the increased pressure of that second pump kicking in. So have a little think, what can we do now to try and mitigate those bursts going forwards?
I just wanna make sure to pause and see if people have any ideas, some unique ideas, maybe. Like my immediate thought is noise loggers or leak detection. But we also talked about condition-based sensors.
Mm,
Oh, nice,
absolutely.
Joel, right there, condition assessment.
Yeah, brilliant. So you're absolutely right. So the first thing I've put in here is we can also install higher frequency pressure monitoring on the pumps to look for any transient activity or pump surge, for example. We know that it's going to be stressing the pipe. If we can get rid of that, maybe it'll help a little bit. Exactly like you said, we can go into the pipe itself and we can find damage. We can look at the pipe wall thickness. We can look for any leaks using some of the sensing equipment we've got there. And on top of that, and this is something that we ourselves have done, is we can also look at the type of soil that the main is laid in and see if that's contributing to the damage on the main's integrity as well. So we find some other key areas where the pipe is about to burst and was leaking significantly, as well as many more places where the main is weakening but not yet leaking. The high frequency pressure monitors show you that when the pumps turn on and off, there's a significant slam from the non-return valve closing, as well as a large pressure surge as the flow gets up to its steady state. We choose to repair the sections of main which were leaking, but we need to maximize the lifespan of the main because this was an expensive problem to have. How can we extend the longevity of the main through control alone? And again, yeah, if you've got any thoughts, pop them in the chat.
So I suppose that would be a pump control, or maybe not, because this is the beacon. I mean, I think this is a condition assessment thing. Or I suppose velocity and water quality. I'm lost.
It's fine. So the thoughts that I had around this, since we're looking at just that control, I suppose one thing I've not said in here is we don't have the money to replace the entire main, unfortunately. But we can look at ramping the pump starts and stops to try and reduce that pressure surge, try and get those pressures down at least to hopefully prevent a burst, at least in the short term. We could maybe control the pumps using a more complex control loop based on the level of the water in the tower, for example. That would completely mitigate the surge problem, and it means that we would be running at the minimum pressure that we needed to be, potentially. And we could change the non-return valve out for an actuated valve and control it to open and close automatically rather than getting it to do it based on the flow rate going through, because we can see that there's a lot of slam coming from that non-return valve. So these are some stuff we could do specifically for control, but you're absolutely right. The solution here is replace the main with something that's not going to corrode in the soil that it's in. But unfortunately, yeah, the main laid in the ground was damaged by the soil. It's too expensive to relay the entire main at the moment, unfortunately. So we put in a more complex control system, not least because it's the safest and the easiest to install. Doesn't require us digging. It doesn't require us working around customers' houses. It's entirely on site. In the end, all the major leaks on the upstream side of the tower get fixed. And the pumps now run more or less how they did before, albeit controlling the level in the tower to a much tighter range now. So in retrospect, a system approach may have provided the answer more readily. How could we have done it differently by taking a system approach, do you think? And with that, could we have avoided the situation entirely through proactive monitoring? Is that something that we can put in place for DZs in the future? This is a really big question that we've got within the industry at the moment, is what can we do to stop it getting to that position? What can we do to stop those interruptions to supply or those bursts? Because it's not good for anyone. It's not good for the utility. It's not good for the customer. If we can avoid it, it's not good for the environment. If we can avoid it, we absolutely should.
So I just want to jump in here real quick. So basically on the last slide, we went back to the very first answer from Ash, which was what data do we have currently? And I think that pretty much answers this last question is what could we have done it differently? Well, we could have looked at our own data that we have, and we could have probably increased proactive monitoring on it if we saw any data gaps.
Absolutely right. Yeah, that's 100% it. Now, especially now where we find ourselves with those sensors, we have visibility of pretty much everything from the pumps downstream, and it's granted not water quality in the same way, but yeah, exactly that. We now know the situation the network is in. At least we have a better understanding of the situation the network is in, so we can start to proactively plan it. We can start to make changes to our network that really enhance how it operates, not just making sure it works day to day. You're absolutely right. So we'll touch quickly. I'm just conscious of time. We'll touch quickly on wastewater and stormwater. So this is a comparison between your wastewater and your stormwater sort of collection systems and let's call them networks systems. Ultimately, we're still trying to measure similar things. It's just they, like we said, have different goals. So in your wastewater system, you can see there's very strict compliance around effluent discharges. There's a lot of regulatory it's very regulatorily strict. Whereas with your stormwater, ideally, what we're just going to be moving is raw water, is rainwater, and the runoff that comes with it. So it's really about moving that water to where it's not going to cause a problem, or it's not going to flood, or it's not going to damage an ecosystem. Um, One of the other big differences there is that your wastewater system is continually operating. We're always going to be producing some kind of wastewater, but your stormwater is very much event driven. So when it comes to then the focus of those sensors and the focus of those controls, it's actually your wastewater is much more about making sure that we know what we're pumping, we know what's coming down the line, and we know how we're going to be cleaning that and making sure that it's safe to put it back into the environment. Where your stormwater is actually, do we know what's coming? Do we know how much rain? Do we know how much we're going to have to change the way our treatment work operates in order to cope with the extra demand it's now going to have? But ultimately, we're going to be using roughly the same set of sensors, albeit in different functions to do sort of similar stuff. So to close us out then, and just to sort of tie it up in a nice bow, we can, in theory, measure and control pretty much every point in our water cycle. In practice, like we saw with the example earlier, there are definitely some restrictions, and the big one is cost. Um, we also need to be conscious that where we're trying to put this sensing and control, it may not be safe. It may not be easy to access. We may not have the personnel who's able to install it. They may not have the relevant training. They may not have the relevant equipment in order to install it. And a really big one that we spoke about earlier is that trust in the data quality as well. Making sure that the people who are going to be using that data trust it and feel comfortable that it will give them the information that they're looking for. Now, a really key point here is not everything has to be automated. Absolutely, like I said earlier, running a pump in hand, going and manually twizzling the PRV set point, or going and opening or closing a sluice valve in a road, absolutely is still your control. And going and taking like Nascari said, opening up your tap, taking a water quality measurement then and there, that's still sensing. Looking at a gauge, it's still sensing, but it's all done manually. And it's still just as important that we are aware of it, and we make sure that it's taking place and we trust it, and it follows those sort of paradigms that we've been putting in place all the way through the conversation. And as we were saying earlier, what we can't measure, we can calculate. generally. Things like your leakage, we may not be able to measure exactly how much water is coming out of a specific hole in a specific pipe, but we can see how much water's going in and we can see how much water's coming out. So we can calculate the difference between those two if we trust the data that we're doing it from. And like we were saying with the different kinds of hammer and a nail, look at the type of sensing and control you want to put in place. Is it the right kind of sensing? Are we trying to use a sledgehammer to put a nail in a wall, or are we actually using a proper hammer to do it? Do we need to have it in place? A lot of sensing and control can be expensive. Maybe there's a better way, a more cost-effective way that gets you what you want, but maybe it's not got some of those nice to have features, but ultimately it fits the bill. And you can see there, pick the right tool for the job. It's also well and good going, oh well, I need to hammer this nail in, but you definitely don't do it with a screwdriver. You definitely don't present someone with something that's completely, if you want to measure pressure, you get a pressure monitor, not a flow monitor. If you want water quality, you get a water quality monitor. Sometimes it's not as cut and dry as that, but generally making sure you pick the correct tool for the job is really important, because otherwise that tool, it's just not going to be used. So that is everything. Thank you ever so much. I've really appreciated the opportunity to discuss this with you all today. If you have any questions, please do ask now.
That was amazing. Thank you, Alex. I know Dan
Thank you
asked
so
one
much.
question, which we pretty much answered through the exercise.
Yeah, should we
I'll-
ask away?
Please do.
Yeah, go ahead.
I asked it and then you answered it in the next slide. So good thorough presentation, Alex. It was actually really super interesting.
Thank you so
Thanks
much.
for sharing that. My question was, do we consider non-fixed assets as part of the sensing and control layer? So I know the options I gave were like a pipe bot or like an insertion probe, like a Sahara survey, or CCTV insertion probe or something like that. So and then you did go ahead and answer that was a part of this layer. So that's great. But I don't know if you had any thoughts on that at all that you might want to share in more depth.
Yeah, no, I think it's a really, really good question to ask. And as far as I'm aware, we absolutely do. It's still about understanding the situation the network finds itself in. And in terms of then bringing it up to those sort of higher levels, that 4 and that 5, we're still absolutely displaying it alongside, say, acoustic leak detection data or something. So yes, I believe so. Because sensing is sensing. It doesn't matter whether we're doing it once off or whether we're putting something permanently in place. It's still sensing.
Yeah, I think I agree with you, Alex. That was my thought too, and I think it poses some I guess other ideas around this topic in terms of you've spoken a little bit about strategy and using the right tool for the job. For the record, I have used a screwdriver as a hammer before, and I don't recommend it. It wasn't very efficient. But yeah, if you think about certain things, like you might buy assets to lift and shift for specific use cases. Like I know, Naisagi, you are a modeler by profession. I know certainly our modelers at Thames will lift and shift sensors to help calibrate a model. It would be a good example of that. But there are other things as well. Alex, we're certainly still working with your former employer on transient monitors, and some of that program involves lift and shift. But what's quite interesting is the approach that Josh, who's our calm systems leader, has taken, is that you might put out a fleet to begin with, and then once you've resolved the problem, you might leave what we might call a shepherd sensor that's still there just to check that nothing has ever deteriorates, but you take the rest of the fleet on to the next challenge. So I do like that concept of when you're looking at your sensing and control strategy for a hydraulic system, that it doesn't have to be a fixed thing, especially when you're talking about costs, power, comms, maintenance, and all of the baggage that comes with it. Actually, it's that you should probably have a core set of kind of fixed assets that are giving you that, but acting as that shepherd and giving you that early warning and some of this stuff. But you don't have to have the whole shooting match there all the time. You can bring stuff in, gather some data, and move on.
Yeah, you're absolutely right. And this is something that we do within Anglian to a certain extent as well. Is take the transient detection work. Often it involves a lift and shift high resolution logger that goes into a location that experiences lots of transient activity. But part of the way that we know that is through that, like you say, that shepherd or that watchdog logger that's going, actually, we can see something's picking up now, so we should go and have a look in this place. We should go and have a look here, here, or here. So yeah, absolutely right. One thing that I'll be very quick. One thing that I didn't realize, but absolutely makes sense now that it's been put in front of me, is that in terms of that layer 1 as well, we have mobile PRVs. We have temporary PRVs that we install in our network. So I guess even your level 1 can have temporary. It's still layer 1, but it's just a temporary installation.
The other thing I'd say about layer 1 that we're learning through retrofitting the hardware from decisions from the past is that if you are installing fixed sensing assets, that you should probably build in some redundancy. So when you do inevitably have to do some replacement or maintenance, that you don't cause major kind of system outages or problems because you need to shut pipes or whatever to remove and replace assets, and instead have things like bypasses or indeed mobile PRV options, so hydrants that will allow you to do that, for example.
Yeah, absolutely. No, it's interesting, especially working in a utility that's been a utility for a very long time.
Yeah, absolutely. It's a very interesting time capsule, that's for sure.
That's certainly true. Cool. Are there any other questions before we?
I don't see any in the chat. So I think we can wrap it up. Unless I'm missing someone, please feel free to speak up. But yeah, thanks everyone. Right on top of the hour. Great conversation. Great exercises. And I'm probably going to go back and revisit the exercises. It was a little too fast for me to keep up because I think for what I do, it almost seemed like 10 engineering projects right there.
So yeah, sorry. I did speed through it a little, to tell you the truth.
No, that's definitely really helpful to think about, because it's like, yeah, I can learn about a sensor, but if I don't know what it does and why it does what it does, then what's the point?
Yeah.
So
thank you all ever so much. Really appreciate the opportunity.
yeah. Well, thanks, Alex, and thanks everyone for joining in.
Great. Thanks, guys.
Cheers, guys. Thank you.